It is my great pleasure to introduce to you our very first plenary speaker, being Dr. Jiri Marek of Robert Bosch in Germany. The title of his talk will be MEMS for Automotive and Consumer Applications. Dr. Marek studied electrical engineering at the University of Stuttgart and Stanford University. And in 1983, he received his PhD from University of Stuttgart and Max Planck Institute. After a postdoctoral fellowship with IBM Research in San Jose, California, he was a development engineer with Hewlett-Packard, and in 1986 he started his work with Robert Bosch in Reutlingen, Germany. Since December 2003, Dr. Jiri Marek is Senior Vice President of Engineering Sensors at Bosch Automotive Electronic Division, where he is responsible for MEMS activities at Bosch. Please join me in welcoming Dr. Jiri Marek.
Thank you. Good morning, ladies and gentlemen. It's a great honor for me to start this conference with my presentation. The title of my talk is MEMS for Automotive and Consumer Electronics. 78% of all cars have a pressure sensor made by MEMS. 90% of all cars produced have a MEMS acceleration sensor. 28% of all new phones have a MEMS acceleration sensor. And every fourth digital camera has a gyroscope also made by MEMS. As you see, there are MEMS sensors everywhere. In my talk, I would like to introduce you to this field and give you an overview. I will start with a short introduction, show you some specialties on MEMS manufacturing and MEMS development. And then later on, I would like to discuss two topics more in detail, which are yaw rate and acceleration sensors for vehicle dynamic control, as well as consumer application of these devices. And I will close with a short outlook. So for the introduction, what is MEMS actually? A short history of MEMS and some data on the market. MEMS stands for Micro Electromechanical Systems, which are systems which are containing a mechanical structure with dimensions on the order of micrometers, together with an electronic structure, combined onto a single substrate or even on a chip. On the bottom, there's one example, being an acceleration sensor. The micromechanical structure is shown over here with a high complexity of different beams, as you see over here, on the order of microns, and associated electronic circuit for evaluation and trimming to the right. Why use silicon for sensors? Besides the excellent electronic properties, silicon has also very good mechanical properties. Silicon is 3 times lower in density, but it has 4 times higher yield strength. Silicon is 3 times slower in thermal expansion. It's a single crystal material, and therefore it's brittle. We have no plastic deformation. On the bottom, you see some structures made out of silicon. These have the rings, so with the tweezers they can be deflected, and you see what kind of big deflection movement we can actually do on these silicon structures. So with this, I would like to show you a short history of MEMS. It started in 1970 with a resonant gate transistor with a metal beam micromachining. But very soon, the researchers realized that the deposited metals onto silicon are not very good in terms of the mechanical properties, and people switched to silicon. So the first MEMS sensors made by silicon, by Coolite, Stanford University, and Honeywell have been realized in the 70s. Here's a picture of the first micro beam mirror. It's a MEMS scanning mirror made by Kurt Peterson at IBM in 1980. At the same time, Professor Sessler at the University of Darmstadt in Germany realized even the first MEMS microphone. The first killer application with very high volumes was the introduction of inkjet and the inkjet nozzles made by micromachining. The examples are the HP ThinkJet and the bubble jet by Canon in the 80s. There was then a rapid introduction of different devices then in the 90s. Here you see the integrated accelerometer made by Analog Devices, which was realized in 91. A fully integrated single chip accelerometer, evaluation circuit, trimming and sensing on one chip. A gyroscope followed soon. This is the Tuning Fork gyroscope, which has been made by Draper Labs in 1993. Texas Instruments had a very long research on DLPs, on digital light processing, and here you see the pictures of these devices for projection from 1994. And at the same year, Bosch invented the deep reactive ion etching process, which is capable of making very deep and very precise structures out of silicon. For ESP system in 1998, the first gyroscope came into mass production for automotive applications by Bosch. 2003, we saw the tire pressure sensor system made by Motorola. And by the year 2008, Bosch was the first company to announce to have over 1 billion sensors shipped into the field for automotive applications. So as you see, the market came into different waves. First applications started in the 80s. The first high volume was then the inkjet printers in the middle of the 80s, followed by a big increase of automotive electronic applications. Then the digital light processing for projection. And since a couple of years, we are seeing a rapid growth in consumer electronics with many different applications. Here's the view of the market as supplied by the iSupply Corporation. We had a peak in 2007 with $6.5 billion in the market volume. Obviously, as everybody in the industry, there was a dip by about 10-15% due to the recession 2008-2009, but we are looking for a rapid growth in the years to come. The main drivers, the biggest single market, are the inkjet nozzles, followed by the different sensors, like the acceleration sensors and the pressure sensors being the two biggest one, and then the displays, which is the third big portion. So after this introduction, I would like to show you some of the specialties of MEMS manufacturing. I will introduce you to surface and bulk micromachining and show you the challenges of this technology. Bulk micromachining, as the name says, we are making the structures out of the bulk silicon by selective etching, so the structures are monocrystalline. Here you see the schematics. The silicon as a single crystal has etch rates which are different depending on the crystal orientation, and therefore we can make cavities and membranes using the different etching rates of etchants. For example, the 100 direction is generally etched very rapidly, the 111 at a very low speed, and therefore we can make cavities, holes, and nozzles into the silicon. The second technology, which has been introduced in the 19th, is the surface micromachining. In this technology, the structures are made on top of the wafer by deposition and selective etching. The structures are generally made out of polysilicon and silicon dioxide, and so we have few contamination risks, and we can integrate this technology very well into the semiconductor processes. Also, some of the technology steps are shown over here. We take the silicon substrate, deposit a sacrificial oxide, shown in yellow on these cross-sections, and onto this a thick poly. This is mostly deposited into an epitaxial reactor, so we can achieve high deposition rates and have a very good mechanical material. The typical thickness is 10 or 20 micrometers. The next step is to etch the mechanical structures by etching into the depth by the deep reactive ion etching, and very perpendicular walls with high aspect ratio and very good lithography deposition precision can be made by this process. The last step is then the removal of the sacrificial oxide of this yellow layer, and you see some of the polysilicon has been deposited directly onto the substrate, so it's fixed, it's anchored to the substrate. The other parts are freely movable, so we can make fingers, bridges, masses, etc. onto the wafer. Here you saw one of the examples, which I will discuss a little bit more into detail, which is a gyroscope for the electronic stability control. You see it's a very complex structure, and on the right you see some of the details. We can make electrostatic fingers, we can make blocks, we can make all the structures which is necessary for this complex device. Another example of the surface micromachining is the advanced porous silicon membrane technology. For this technology, we are using anodic etching to generate porous silicon. The density of this material is very small, and therefore, as we go into a sintering process, this material will collapse. We have a membrane, which is a seeding layer for epitaxy, and with the epitaxy, we can grow a very good monocrystalline membrane with excellent semiconductor properties on top. And as you see, by the porous silicon, which was on the bottom, we've been able to create a cavity with a vacuum below this single crystal silicon membrane. And here you see some of the examples. On the right, a cross-section with the substrate, the vacuum cavity where the porous silicon was before, the membrane, and the piezoresistors then manufactured on top of it. On the left, an example of sensors with a membrane in the middle, the amplification and the trimming circuit then on the periphery. You are very familiar with the semiconductor processes. So what is the challenge of MEMS? As I showed to you, we need some dedicated process steps and therefore dedicated equipment which has to be developed. For example, the HF vapor etch for the sacrificial oxide removal, so there is no sticking, and the deep reactive ion etching to make the structures into the depth of the silicon. Some of the processes have contamination risks, like the anodic bonding and the anisotropic etching by KO etch, and therefore we have to take special precautions in terms of designing the processes and the sequences. The sensor is a combination of electronic and mechanics, and therefore we have to combine the mechanical and electrical parameters. We have to make a design which is both a mechanical and electrical design, and that makes the design process much more complicated. The mechanical sensors generally would have a strain gauge. They are like the piezoresistor or a capacitive pickup, and it has a displacement. And therefore every strain, mechanical strain due to packaging, will also influence the parameter of the sensor, and we have to take into this account by design and also by controlling the mechanical stress of the package onto the device. It's a sensor, and therefore by the end of the fabrication, we have to test physical parameters. We have to put pressure onto the device, we have to put acceleration or yaw rate. And last not least, these sensors are going into application, into media like pressure or airflow, and therefore we have to design the assembly and the manufacturing in order to have the robustness and the media compatibility of these devices in respect to the application. So some of the MEMS roadmaps over the last decades. Here you see the trend in the package following very much the trend of the semiconductor industry. The first acceleration sensor started in the 90s with BLCC packages, and the footprint was on the order of 150 millimeters square. You see here the rapid decrease of the size, then the SOIC packages, and also now the QFN packages, which have been introduced over the last years, making the footprint drastically smaller. We are very proud that we announced a week ago the volume production of the next 3-axis sensor, which is packaged together with the associated electronics in a 2x2 QFN package and is the smallest sensors at this moment. The trends on the associated ASICs, also very similar to the rest of the semiconductor industry. The analog part has a complexity of several thousand transistors, but in this case is remaining fairly constant over the years. This is due to the trend that most of the electronics on the evaluation circuit and also on the trimming and digital signal processing has been transferred to digital part. And therefore, for example, for the ESP sensor, the first one introduced in 98 had almost zero digital content, and now, 10 years later, has over 1 million transistors on the same chip. Here I would like to show you the capability of these sensors. As an example, this is a 3-axis acceleration sensor made by the Bosch SensorTech in a 3x3 package with a digital preprocessing onto the chip. And this sensor is capable in the 3-axis to have a resolution of 0.25 millig. So if you compare this with an airplane having 45 meters of a wingspan, we can detect 5 millimeters tilt on the sides of the airplane, just to make the resolution of this device really realistic. So over these trends, I would like to show you 2 devices into more detail. The first one being the yaw rate and acceleration sensor for vehicle dynamic control or the electronic stability program. So I will show you a little bit about the working principle and then later on some of the results of these devices. Let me show you in the beginning the ESP system more in detail. Here in the video, the ESP system improves the stability of the car very drastically and makes the driving safer. Like for example, in this situation, you would have an obstacle on the freeway, have emergency change of the lane, which would actually make the car very unstable. You see, you have to change the lane to the left. And for that, the system, and that will be shown over here, it consists of different sensors. In order to measure the speed, there are the wheel speed sensors located on each of the wheel, a yaw rate sensor measuring the rotation of the car along the perpendicular axis, and the steering wheel sensor measuring the steering wheel input of the driver. In blue are the hydraulics, which are then activating the brakes on all the 4 wheels individually. Now, as we have this driving maneuver, the driver will turn the steering wheel to the left. He wants to change the lane to the left. However, the car is continuing on the right lane straight. The yaw rate sensor measures a gap, and therefore the system will put a braking onto the rear left wheel in order to increase the momentum to the left of the car. This will help the driver change then to the left lane and still drive the car safely. Then as you go to the left lane, the car would actually oversteer without the system, and it would, because of this momentum, it will start skidding. The system detects the movement on the back of the car, puts a braking on the front left wheel and therefore stabilizes the car and keeps it then on the left lane without breaking out of this curve. So as you see, with such a system, we can improve the stability of the system under these conditions very drastically. And therefore, the NHTSA made the regulation to make these systems compulsory. I think after airbag in the 90s, the second big movement in order to make the cars more stable and more safe. Such a system is only possible if we can measure the dynamics of the car, the movement of the car in a very precise manner, which means that we have to measure the rotation along the perpendicular axis with high precision, and this we have to do over all the conditions, the temperature from -40 to plus 125 degrees C, and also with all the vibration and conditions in the car. The first systems started in 1995 with a mechanical system. It was a high-precision mechanical cylinder which was put into rotation, and the very elaborate trimming and associated electronics were contained in this package. Therefore, in 1998, we introduced a combination of bulk micromachining and surface micromachining to realize the first automotive yaw rate sensor. The first generation in 98. The second generation followed in 2005 with pure silicon micromachining, and this technology enabled us to make the device much smaller and also more cost effective. The next generation was then in 2008 with even a further decrease of the size. Some of the customers like to combine the hydraulic and the electronic system into one device, one package, and therefore we have to put the yaw rate sensor also onto the hydraulic, which was the next generation, which was the first integrated ESP sensor system. And in 2010, we are now combining even the acceleration sensor for the longitudinal and transversal acceleration into one package. This device will come onto the market this year, and it contains the yaw rate sensor, being the bigger surface micromachine chip, the acceleration sensor, a smaller device, and both of these are mounted onto the ASIC, which is then combining them also mechanically with the connections and then the circuitry connected to the outside. Some of the details on this device are shown over here. We are using the surface micromachine process with a polysilicon layer of 11 microns. The packaging, the first level packaging, is done by wafer level. So we take a second wafer, bond it to this device, so we can realize hermetic sealing at the wafer level and have at the same time a vacuum encapsulation of 3 millibar, which is necessary in order to drive this device with the electrostatic force drive. The system is driven at 15 kilohertz, which is the first resonance frequency of these plates. It's driven into an anti-parallel motion, and it's coupled by mechanical springs. With this, we have a more mechanical robustness because the center of gravity, due to the anti-parallel motion, doesn't move, and therefore any vibration from external will not change the performance. We have a high Q factor, which provides us with high biostability and noise performance. And due to the excellent performance of the MEMS processes, we have tight mechanical control. Therefore, we have mechanical crosstalk at a minimum. I would like to show you the working principle in more detail. You see these two structures, symmetrical on the right and the left. And they consist mainly of three portions. In the red is the drive frame. We put the electrostatic deflection to the front and to the back. And with the alternating voltage, we can put the whole thing into the resonant frequency. The next step inside is the Coriolis frame. So the structure is capable of deflection in the direction of the Coriolis force, which I will show just in a second. And in the middle, the gray part, is the detection frame consisting of many different fingers, because the signal is very small, and therefore we want to have a big capacitance for detection. Here you see a video of the function of this device. Inside the ECU, which is located in the middle of the car, is the microprocessor and the drivers, as well as the sensing portion. The yaw rate sensor, as I showed you, due to the drive frame, is then oscillating anti-parallel to the front and to the back. The yellow is the Coriolis frame, and the detection frame in the middle, which is capable of moving to the right and to the left. So this whole movement happens at 15 kilohertz. You see the same driving conditions. The system is symmetrical. As you now start to move the car to have a rotation, there will be a Coriolis force, which is in the direction to the right and the left, and therefore the detection frame will move, and we have a capacitance change, which will be measured by the associated electronics. I would like to show you the principle of the evaluation circuit, which is a very sophisticated device with lots of analog and digital parts at high sensitivity levels. First of all, we have to put the system into the oscillation. So we have the driving circuitry. We have a pickup on the sensing element, a C to V converter, and immediately after that, ADC, so we can go to the digital portion. There's a PLL loop and a gain control and a feedback loop, so we get this device working at the first resonant frequency with a constant amplitude. The Coriolis force is then detected by the sensing element, which I showed you before, inside frame. Also, a very precise capacitance to voltage converter as the first step to go to the digital domain, a ADC, digital filtering, which is necessary, and then a summation, a multiplication. We have a temperature sensor, since we need a very wide temperature span for the automotive application, which provides us data for adjustment. We add this temperature compensation. We have output filtering, which is necessary for this application, an amplifier, and the SPI protocol, then to go into the microcontroller for the system. There's an internal built-in testing. It's a vehicle dynamic system, therefore the reliability requirements are very large. So we have to go and test the system at the requirement of the system designers. We have an electrostatic test on the plates of the sensing element. Then this deflection goes through the whole of the electronic circuit and the digital part and gives us an output, which is then measured. So with this built-in test, we can verify the performance both of the MEMS part and of the electronic part at any time. Some of the features of the evaluation circuit: we have a very low noise analog front end. The circuit is highly digital, so it's an early A to D conversion, provides us with a very low drift, and all the signal processing is then done on the digital level. There's an advanced control loop for the detection path with a fourth order electromechanical delta sigma converter. The noise shaping with a bandpass characteristic eliminates then the noise on the signals path, so we have a very good signal-to-noise ratio. I would like to show you some of the typical measurement results on this device. In terms of the bias stability, as you see, we have with the different measures over here in the analysis, we have a bias stability of 1.3 degrees per hour, instability on better than 3 degrees per hour. So for such a small device on MEMS, we think that this is very outstanding performance. In terms of the noise, We see a white noise characteristic with a passband performance. There's a digital low-pass filter, and the excellent noise performance then results in typical values of 4,000 of a degrees per second per square root hertz. Also an excellent value for high volume production in the automotive. I would like to show you the noise and the resolution limit and compare them a little bit what the device is actually capable. The resolution limit is on the order of 3 degrees per second, 3 degrees per hour. So this corresponds to an amplitude change of the micromechanical structure of 4 times 10 to the 15th meter, which would be about the distance of, not of the silicon to silicon distance, but actually of the atomic nucleus. If you look at the capacitance change, as we do the integration, we are capable of making a resolution of 2 times 10 to the 21 farad. So this compares to about 0.06 electrons at a 5-volt supply voltage. So after this system from the automotive area, I would like to show you some of the consumer applications of MEMS. Over the last couple of years, we saw a rapid increase in the application of acceleration sensors and pressure sensors into mobile phones. You can do the menu input and the position and motion change detection. In the gaming, there's a completely new experience by the human motion interaction of this device. So these devices are very popular. The mobile computing, I think most of you who have a laptop here, you will have an acceleration sensor for the free fall detection, protecting the data on the hard disk drive. In the case you drop the laptop, the read-write head will be retracted, and the data is then saved and is not damaged by the fall of the laptop. Sports and fitness, monitoring of step counting and altitude. Some of the use cases on the phone is shown over here. The user interface, the tap control of the functions on the mobile phone, gaming input or a menu navigation is performed by the movement of the mobile phone. The position detection, you can do upside down mute, for example, with the acceleration sensor. The change between portrait and landscape, also popular on digital cameras, or a free speech profile, where you see how the mobile phone is moved to your ear and you do an automatic pickup of the phone call. Motion detection for step counting or activity monitoring. Power management, pedestrian navigation in the future, where you take the acceleration or the yaw rate to assist into the navigation, measuring the speed, distance, and also the altitude. So, with this, let me give you an outlook. What's in the future up for MEMS? We see a whole bunch of new MEMS devices approaching on the market. For example, a MEMS autofocus for cell phone cameras. Energy harvesting with electronics consuming less and less power and MEMS capable of having movable structures. We can generate energy and provide an autonomous energy supply. Micro fuel cells, there's research going on to integrate these into silicon and make low power generation. Or micro mirrors to do a micro projectors so you can have a mobile devices and projection of your slides or movies whenever you would like to. But also fusion of the different MEMS is another trend. 9 degrees of freedom, inertial measurement unit, will be realized in the next years. So we will take a 3G accelerometer, combine it with a 3-axis gyroscope, and put a 3D magnetometer on the same chip, so we can measure the movement of the device for navigation for all the possible combinations into one unit. Or wireless sensor modules. combining different sensors, putting a RF module onto this device, combining with an energy harvester, then we can place wireless sensor modules in different places at a very small package and combine them into sensor networks. So with this, I would like to summarize two major applications, the automotive and consumer on MEMS. MEMS is a main driver for the sensor development in the automotive industry. We have a constant enhancement of the MEMS technology, giving us smaller and smaller devices, combining components and realizing new functions as well. This is a continuous development of this technology with new devices and shrinking, like in the semiconductor field. In terms of the consumer electronics, MEMS was even the enabling technology for sensor application, because the sensors made at a micromechanical way would not even fit into the mobile devices. And therefore all the new functions in the mobile devices are realized by this technology. The key factors are size, making the devices smaller and smaller, decreasing the power consumption so we don't drain the battery, and obviously the price. In future, we think that we will see a big variety of new applications and many different use cases for this technology. Thank you very much for your attention.
Thank you very much.
Thank you.
Thank you. Thank you very much, Jiri, for your excellent presentation.